Hello, everyone. Thanks for joining this session, which is about one of the most interesting, one of the most exciting features of C++20 concepts. I'm sure you've seen that concepts is one of the prevalent topics of this conference, CppNow. Yesterday we had 3 hours of concepts with Jeff Garland, and tomorrow there will be another other presentation by Andrzej Krzemienski on some more advanced features, more advanced considerations of concepts. Today we are going to speak about the basics or the concepts of concepts. But before going into the details, let me introduce myself. My name is Sandor Dargo, and I'm a software developer for Amadeus. So I'm working in the travel and hospitality industry. If you've ever booked a flight, most probably, well, there's a fair chance that you went through our services. In my free time, I write a lot, mostly on my blog about C++, about books I read, or about how we can apply Stoic philosophy to our craft. I used to be a passionate traveler. Well, there's not so many options these days. We hope it's going to get better, and I'm experimenting with sourdough baking with my 2 little very active kids, but that's more than enough about me. So let's have a look at the agenda. What are we going to talk about today? So first, we are going to cover why do we need concepts at the first place. Then we're going to see 4 different ways to use concepts with functions. This part is mostly about the syntax. After, we are going to see how to use concepts with class templates, and after, we'll see what do we already get with the standard library of C++20. And then, well, that will be, I think, the longest part. We'll see how to write our own concepts, and we will finish with some real-life examples of how concepts can ease our life, how concepts can make our applications more maintainable, better documented. So let's start with why do we need concepts, and what are concepts at the first place? So I'm sure that most of you know that concepts is one of the big 4, one of the new major features of C++20 along coroutines, modules, and ranges. It's an extension for templates, and it helps us to validate template arguments at compile time. But why do we need that compile time validation? So I'm going to use, say, a quite simple example of a function called add, which has a simple aim. It wants to add 2 parameters. It wants to add 2 numbers and return their sum. And let's see how we could have this. So let's say you want the function add to support different types. And well, we could use overloads. You see that we have an overload for ints, we have an overload for long doubles, but we could have many different overloads. And one thing is that it's really tedious to write them all. And at the end, it's quite verbose, and even worse, it's really difficult to maintain. So obviously, this is this doesn't scale. This is not a good choice. So what else do we have? What other options do we have? We could use templates, and well, It's not bad. Probably it's better, but templates will allow just really anything. You have no constraints on, well, no obvious constraints on the types accepted. And you might have to face some behavior that you don't really expect. So if you look at the example, you see that in the beginning, well, we had two integers, 42, 66. It will work as expected. Then we have some longs, and then we have two characters. Now, what would you expect by adding two characters? Well, I don't know what you would expect, but probably what we get is not really what we want. That these characters, first they are casted into integers, and then their sum is casted back to a character, and at the end we receive something not really meaningful. So the problem with these templates is that in many cases you won't get what you really wanted, or you cannot really constrain how others can use your functions. So did we have some solutions for that? Well, we could forbid some template specializations. Like on the example, you can see that well, we simply delete the specialization for strings, and then you cannot make that call that you can see in the example. You cannot call add with two strings because it's deleted. Problem is this doesn't scale. So with how many types do you want to forbid the specializations, or do you want to forbid only for built-in types, maybe for all the other user-defined types? Well, this doesn't scale. There is a better solution. We could use type traits and then static assert, and we also get hopefully nicer error messages. I say hopefully because with static assert it's you who defines these error messages. You have a bit less overhead than before, and everything will be at one place. And instead of forbidding certain types, you go the other way around. You make some expectations, but still, it's not intuitively and not easily reusable. So here comes concepts to rescue, because they provide a readable, scalable, yet reusable solution to constrain the template arguments. So here you see a simple example for a concept for built-in number types. Well, we'll see that this is not complete. It's for the sake of example. You have a number that is either an integral or a floating point, and you can say that you're in your template function. You want to have t's that model the number concept, that satisfy the constraints of the number concept, and that's how you can use it. So at the end, concepts will make templates more safe, and they make generic programming more scalable. Like, what do I mean by that? Most probably, many of us had discussions in our teams where people complain that, okay, please don't introduce templates because they are difficult to understand, they are difficult to debug, and we cannot really constrain how others will call the templates. So please avoid that. And with concepts, well, you can win that argument. It's not about winning the argument, but you don't really have this problem anymore. And we'll see that concepts also allow putting more domain knowledge into code. So you have these very important advantages of concepts. Let me check the Discord and the chat and the questions. Okay, so let's have a look at the 4 ways that we can use concepts with functions. So I mentioned that we have this concept number that models only the built-in numbers, but it's still incomplete. We'll see why at the end, but for the sake of example, we are going to use this concept number. It fits the screen easily, and it's something that that we can comprehend well. So the first way of using concepts with functions is the so-called requires clause. So you can see that after the template parameter list and before the return type, we write the keyword requires and or different, well, in this case, a concept to be satisfied, but all the different constraints that we might have. And you can combine here different concepts in many different ways. I put there a small asterisk because there are some rules that we'll check later together, and we can combine not only concepts but different different other constraints. We can have different Boolean expressions there. We are going to see the details a bit later. So in this case, basically we inline the concept number. We say that t must be either an integral or floating point. The point is that you can use this kind of combinations, and you can also have like multiple you can also constrain multiple parameter types. And if your concept, let's say, uses multiple types, you can also use that one. So why this is important here? It's important because let's say that well, we go back to the previous example, and you want to use add with an integer and with a floating point number at the same time, then this will not compile, because A and B must be of the same type. Even though both int and say a float will satisfy these constraints that you have here, they must be of the same type. So this won't compile. But in that case, if you want that, you have to use 2 template parameters, and you have to write the constraints on both of them. So function calls happens as usual. You have some, I think, nicer error messages. Now I cut out some parts here for better readability, but mostly those were about just like line numbers. But it's rather intuitive. You see that well, there was well, when we try to call with an integer and the double, as I just said, well, there's no option for that. There is a candidate, but the substitution fails because ints and doubles are conflicting types. So the message is quite clear here. So this was the first way to use concepts with functions. Then you have the trailing requires clause. So this doesn't come after the template parameter list, but you have the trailing requires clause after the CV qualifiers, or after just the function parameter list if you have no qualifiers. And apart from that, it's pretty much the same as the normal requires clause. You can have a combination of different constraints. You can have multiple parameter types. And then we have the third one, the constraint template parameter. So you see, this is more terse. We have no more requires clause. Not after the template parameter list, not after the normal function parameter list. Instead, you don't even have a type name. It's replaced by the name of the concept. So you can still have multiple template parameters, but for example, you cannot use concepts that would take multiple parameters themselves, and you cannot use a combination of concepts. So you couldn't say here that well, t must be an integral or a floating point. There's no way to do that. You have to use a named concept. On the other hand, this is a nice and elegant way to define your constraints. And even if you check the core guidelines, it will advocate for using this one. Then the fourth option is to use the abbreviated function templates. So you see, this is the shortest way to use concepts. You have no requires clause at all. You don't even have a template parameter list. So obviously you don't have the type name. You cannot, as you don't have that, you cannot replace it with anything. Instead, you will use the concept name auto in the parameter list. So you must use both a concept name and you have to put there the auto, because well, otherwise, how would you know that number is not a type but a concept? Well, you might know, but you cannot just know. And again, here we have no support for the different Boolean expressions. You don't have support for combinations of concepts. You cannot write that it must be either an integral or a floating point. You must use a named concept here. And an important thing to mention here, that in this case, A and B can be of different types. They can be of, they must be of, they can be of different types. So this might be an integer, this might be a double. There's no problem with that. So how to choose among these four ways? Well, we have a lot of different ways, right? So if you have a complex requirement and it's not a named concept, well, then you have to choose either the requires or the trailing requires clause. You don't really have many options. If you only have a simple requirement, then you can take the abbreviated function templates. It comes in handy. It's really easy to use. But if you have a simple requirement and you want, well, you still want to keep it short, so you don't want to go with, let's say, the requires clause, but you want to control the number of binding types of the parameters, so you don't want to allow that, previous example, add would be called with an integer and with a double at the same time, then you can go with the constrained template parameter. And you might ask the question, okay, we have these four different types, but are they the same after all? And the question is yes. So I checked with CPP Insights, and well, here you see how it specializes this add with the requires clause. And it's the very same as with the constraint template. The code is the same. Then you have the trailing requires close. And well, it's still pretty much the same. Here appears this requires number in, so you still have the trailing requires close. But I'm not sure why is that. It might be a bug. So I went to Godboard and checked how it is transformed, and you have the very same code for all of these three. And well, there's a slight difference there's an expected slight difference for the abbreviated function templates, because as I said, there the two numbers A and B can be replaced by different types. So we have two template parameters, but that is expected. Apart from that, it's still the same. So you might say that well, this is a simple example. I know, but well, if we take something longer, it wouldn't really fit there. You can go and check on Godboard. You can check on CPP Insights, and you will find pretty similar results for more complex examples as well. So before going to the next section about how to use concepts with classes, let me check the Q&A if there's anything there. So the last way that you demonstrated to use concepts, don't we have to declare the concept before using it? Function declaration with auto. So I guess you mean that if I go back, let's say here, the concept should be, well, defined like, oops, we defined it like here. And the answer is yes, we have to define the concept, but I don't want to include the very same concept on all the slides. That's it. I hope it answers your question. If not, please let me know. Okay, thank you. Thanks for the question. So now let's see how to use the concepts with classes. So here you have a bit fewer syntactical choices, because, for example, abbreviated function templates wouldn't make sense because we don't talk about function templates anymore. And the trailing requires close happens, well, it can appear only in certain circumstances that we are going to see. Probably it's one of the most interesting way to use concepts with classes. But before, let's mention what we still have. We have the requires close. So here is an example like how to use it. It comes after, again, the template parameter list and before the class definition. And again, after the requires, you can list your different concepts. You can list the constraints and you want to be satisfied. And as we saw for functions, here as well, you can use complex expressions. So someone is raising hand. For a function template of two parameters, t and u, how would I express that I want either t or u satisfy a concept and the other to satisfy a different concept, but I don't care which satisfies which? So I would say let's keep this question open, because we are going to see how to write more complex constraints in the next sections. So I will get back to that one if you don't mind. So here we saw how to use the requires clause with the class template. Then let's check the constraint template parameters. You see, this is again a more terse way, but you cannot use complex constraints. You don't have any requires clause. Well, anywhere you replace the type name with a concept, and that's it. So I mentioned that we can have trailing requires clause with class templates as well. So how to do that, and why would you have that? So you might have your class level templates, but you use the concepts on functions. So let's say you have this class my number. I know maybe it's not the most original example, and then you want to implement divide method, and based on the characteristics of this type T, you can provide different implementations. I know this was possible already before like C++20, but now you have a very easy way to do that, because you can simply say that, well, this implementation requires that T is an integral or T is a floating point. So you can provide these different overloads for the different parameter types. And in fact, we'll see that there are some considerations that you have to take into account when you want to provide these different overloads, and when you want to understand how the compiler will choose the right path. So we are going to see that in a couple of minutes. But before that, let's have a look at the standard library, and let's see what do we get, say, in the concept store already. So we have like 50 different concepts in 3 headers of the standard library. You have, probably that's the most guessable one, you have concepts in the header concepts, you have some concepts in the header iterator, and you also have some concepts in the ranges header. So we are not going to see all the different concepts. I'm sure you're happy for that. You can go to CPP reference and check. We are going to see just a couple of these concepts, so you have the understanding, you have the basic idea behind what kind of concepts are in the standard library. So let's start first with the concepts header. In that, you have mainly like 4 different categories. One is for the core language concepts, such as the integral that we already saw, or same as, which helps you to understand if 2 template parameters are of the same type or not. You have constructible from, we are going to see that. You have concepts for comparison purposes, like totally ordered. You have object concepts like movable, copyable, or is it a regular object or not. And you also have these callable concepts to check if something is invocable. Is it a predicate? Is it a unary predicate, or whatever? So let's have a look at first at the Std Default Initializable. It will tell you if a type has a default constructor, if it's default initializable or not. So you see here a simple example. We have 2 classes. We have class A that has this constructor which takes 2 integers, and hence we defined it. It doesn't have any default constructor. And you have class B that has automatically generated default constructor. And when we check if A is default initializable, as it doesn't have a default constructor, the result is false, while for B it's true. So you can have such constraints. Let's see another one. It's constructable from. So I kept the same class A, which takes two integers, and with Std Constructable from, we can check that the type that comes at the first position, if it can be constructed from the rest of the parameters. So you see, we can have as many parameters as we need. And the first one is obvious. From two integers, A can be constructed. With the second example, we see that implicit conversions are taken into account. So A is constructible from an int and the double, but there is no implicit conversion from a standard string to an integer. So the third one, constructible from int and string, it's a false. So we have different concepts in the iterator header. We have iterator concepts like is it incrementable? Is it an input iterator or an output iterator? You have the indirect callable concepts. I know it's not the most comprehensible name, probably indirectly unary invocable, but at least it's quite explicit. And in the iterator header, you will find some other concepts that model some common algorithm requirements, like is a container mergeable? Is it sortable? So you have the output iterator, as I mentioned, and it's a refinement of the input-output iterator. You have to make sure that well, it's an output iterable. It's something writable. You have this indirect unary predicate, which checks if the passed-in type is a unary predicate, like is it callable. If it's a predicate, it should return a Boolean or something that can be interpreted as a Boolean. And as it's unary, it must take only one parameter. So you can see that you can see it with an example here. So on line 12, we define or lambda, which checks if the passed-in number is bigger than 42. We have a vectors, and we just iterate through this vector, and foo requires that what we pass in, well, it's an indirect unary predicate with f that is the function, this lambda function that we pass in, and if it works with the iterator, and yeah, that's it for the indirect unary predicate. So now let's see how we can write our own concepts, and we start from the simplest concept, which is something I call here any. So you have the list of template parameters. Then after the keyword concept, you name the concept, which is in case any, and then you have the different requirements. So in this case, I put there only true, which means that just any t would be accepted. So in case we put here false, then no type would be accepted. But I know we cannot really use this concept for anything, so we should check what other ways we can define in our concept. So probably the simplest thing to do is to combine already defined concepts. So as we saw before, we can say that we have this concept number, and the number must be either an integral or a floating point. And what I want to show with this is that the existing concepts can be recombined, and well, here I used only the concepts shipped with the standard library, but obviously you can use the user-defined ones as well, and well, you can use them in any logical combination with some considerations. What are those considerations? How can we combine these different concepts? So we have to digress a bit to understand that. So what we would usually call and or, they're usually okay, but with concepts, it's better to call them conjunctions and disjunctions because there are some differences, as you will see. But you are free to combine different concepts. You can combine Boolean literals and different Boolean expressions. You can use type traits both with their original form and both with the _v helper functions. And you can combine different requires expressions as well. But you have to understand what negation means for concepts, because there are some differences between normal Boolean expressions and for concepts. So when you consider Boolean expressions, then you take into account that all the sub-expressions are well formed, they would compile, and if they are evaluated to false, it means they would return false. But for concepts, it's a bit different. A sub-expression, it might be something ill-formed. It might return false, but it might be something that simply wouldn't compile. And this works as soon as the whole can be evaluated to true. If not, then you will have a compilation error. So let's see an example for that. Okay, so here we write our requirements that we have two types, okay, T and U, and one of them should have one of them should have a nested type blah that is an unsigned integral. So these different sub-expressions, they don't have to be compilable. They might return false, but they don't have to. So you have different options here. Now let's imagine that you call it with this my type, and then with an integer. So you use my type. It has a blah that is an unsigned int. So this first part is part evaluates to true. So we can short circuit this whole expression, and we say that the requirements are met. We are fine. Now, what happens if you call it with an int in my type? So then we say that, okay, T, which is an int, it doesn't even have nested type blah. So what happens? What happens is that this part is just evaluated to false. We'll consider it as a false, whereas even like int : blah is not well formed. It doesn't make sense. But as long as U has a blah, then or requirements are met. So you might imagine that you want something different. You want to model that both T and U must have this blah, and one of them is an unsigned integral. Well, you can do that. you have different ways to achieve that, and one is to cast this expression to a Boolean, so it's evaluated as a Boolean expression, and then both of them must have this blah, both T and U. Well, I think it's terse. It's a short way to say so, but probably it's not the most comprehensible, because then you need to understand these details that you won't find everywhere about the differences between Boolean expressions and the constraints. So instead, what you can do, you can also use some nested requires expression. And here you can say that, well, for T and U, you require first that both T blah and U blah exists, and then you require, well, what we required originally, that either T blah or U blah is actually an unsigned integral. So probably that's the point where I could go back to that question. So for a function template of 2 parameters, T and U, something that we have here, how would I express that I want either T or U satisfy a concept and the other to satisfy a different concept, but I don't care which satisfies which? Yeah, it's a valid question. Would such a situation ever arise? But let's say that it would. So you can have these more complex requirements, and first you would require that either T or U meets one constraint, and then either T or U meets the other one. I know it might happen that well, actually depends on how you write your concepts and types, how you want to model things. But it might happen that let's say you have T and U, and T models both, but U models none of them. Well, at this point, I think it becomes an implementation detail how to write these more complex Boolean expressions. But basically, with using the concept and using the requires keyword, you have everything that you need in order to satisfy such a requirement, if something like that would ever arise. Let me know if I didn't answer your question. So we still have to understand how to find the most constraint if we have different overloads, let's say in a class, as we saw. So the most constrained one, or the constrained one, will be automatically chosen. So in this case, we have a class ignition, and for the method start, we have 2 overloads. One with the concept requires, and the other one says that the key must not be, one with the smart concept, and the other one says that, well, our key must not model the smart concept. Well, the right paths will be chosen by the compiler, but if you look at this example, there is an anti-pattern here. So if you have 2 overloads like that, then you should remove the negative one. There is no need for negating that. Instead, you can simply use one implementation without any constraints, and the other one with a constraint parameter. What if you have more overloads? The most appropriate one will be chosen at compile time, and what happens here, well, this all happens with something we call subsumption, concept subsumption. There's a very good article about this by Andreas Fertig, and you will find it in the user notes. It's quite a long topic and probably would fit at least half of the presentation. But there are a couple of things that we have to take into account, and here comes negation into picture. So negations might bring ambiguity, and for them you have to use named concepts. But why is that? So as you can see on the left side, we say here that the key must not be smart, and for the third overload we say it must not be starred, but yet it must be a personal key. So when you rely on multiple overloads and subsumption to choose the most constrained implementation, you have to take into account that subsumption rules will take into account the source location of each constraint, and the negation and the parenthesis is part of the expression, meaning that this not smart key between parentheses, and before you ask, you must use parentheses when you have the negation, and this other one has two different source locations, because one is defined here with the second overload, and the other one is defined here in the last overload. So if you try to call with something that is not, with a key that is not a smart key, the compiler will not know which one to choose. So if you rely on such features, you must use some named concepts, even if the core guidelines say that even if the core guidelines say that you should not create unnecessary concepts, you should use the existing ones whenever possible. This is a case when it's not possible, and you have to create your own named concept, even if it will only require that the parameter doesn't satisfy the concept. So let me check here. How can I partially order atomic constraints? We'll get back at the end to it if we have some time. Other than that, we can discuss it later in the Discord chat. Other question, would the requires clause shown here mean that the same thing without parentheses referring to requiring blah and u blah exists? So let me go back to that. Would the requires clause shown here mean that the same thing you mean this one? You must use the parentheses here, because otherwise it's not it's not a simple expression on the right hand side. So here, yes, here, it would basically mean the same thing. Yeah, I put it there for better readability. And which G++ version was used to test this code that supports concept? So I tested this code. I don't know the exact version. I used Qualiru, and I just specified that I need C++20, and it works on C++ reference. You can find the table where it's listed that which compiler version supports concepts, but basically you choose something C++20 and it should be fine. We can check the exact version later if it's needed. So we go to the next section, end of the digression. We go back to see how to write the different concepts. So we can have requirements on operations by something that I call wishful writing. So basically, in the requires clause, you have to write down the operation that you expect to be supported by the template parameters. So here you say that you create a concept edible, and it requires that A plus B should be a valid expression. So here, after the requires, you list all the variables that you might need, and then you write the expressions that you expect to be valid. So here we talk about operations, but after all, it's just a function call. So you can have any requirements basically on the interface. There's nothing that would restrict you from naming any function calls. So here we have, for example, for a simple example, you have has square, and you require that this parameter t should have a function square. Or if it has to take a parameter, then after the requires keyword here with the parameters, you can list whatever you need. So if you need an exponent that is an integer, you put it there, and like this, you can model that t. Well, if it satisfies as power, then it should have a function called it should have a method called power, and it should take one parameter, which we call here exponent, but it must be an integer, or it should be something that can be considered as an integer. So this is nice, but if you consider this square, for example, who knows if it returns void? Who knows if it returns an integer or something completely different? So for sure, you can have a requirement on that one. It's called compound requirement, and you can constrain the return type of the function square. So you must put this expression between this function call between braces, then you use the arrow, and then you can choose among Std convertible to and Std same as. So in one case, you expect that what square returns is something that is convertible to an integer, and in the other case, you expect that it must be an integer. So what you pass there is okay. It's the same as an integer or whatever. You have to pay attention to the braces. They must be there. You have to use the arrow. And if you experimented with older versions of the concept TS, you could use let's say, bare types. You could simply put there an integer or whatever type, but for future generalizations, that idea was rejected, and you should choose one of these template meta functions here. So either convertible to or same as. You can have some other kind of requirements that we call type requirements. So something that we saw that with the example of T and U blah, that a certain nested type exists. You can also model that a class template specialization should be valid, and also that an alias template specialization should be valid. We are going to see one example for each. So you can require that there are nested types. So here I create and write a concept type requirement, and then after the requires keyword within braces, we say that T value type, well, must be a type name. And if you check the example, it means that, well, the standard vector has this value type. So you can create a variable that models the type requirement with a vector of integers, but you cannot do the same, let's say, with an integer, because as the error says, well, this deduced initializer wouldn't satisfy this placeholder constraint because it doesn't have a value type. You can require that nested template specializations are valid. So here we have another type requirement where we require that other with this template parameter T is valid. It names a type. So in our case, I created a struct that requires that T is not the vector of integers. So then if we want to have this my vector that models type requirement, and we create it with a vector of characters, then it will work. But the other one will not work, because a vector of integers, for the vector of integers, the required type other T is invalid, because for the struct other, we require that the template type T must not be a vector of integers. Then we have this requirement on alias template specializations. So here we create an alias for reference, and well, I don't really have a good example for this one, but you can say that this reference T, so using this alias, must also name template specialization. Concepts can also be nested. You can introduce some additional constraints without creating new named concepts. So you are going to see in the next couple of slides that often there's a better solution than that. Often there is a better solution than nesting requirements into each other. If you think about, like, you know, just different loops, often there is a better way than nesting loops. But there are some cases when you need this, so it's important to know that it's possible. So in this example, first we have a concept car, and well, it's something simple. We require that that car has a start engine method, and then You have another concept called convertible, and the convertible should be a car. So that's why we say here that, okay, the C must model the concept car. And we also require that this car has an open roof method. And then we want to define our concept coupe. And well, there are different ways to do that. One is to use a nested requirement. And we have a requires clause, and then we have a nested one. Because when you use this other concept within here, so we say that the coupe must be a car and must not be convertible. I know that it doesn't really mean that that it's a coupe, but at least it's not a convertible. So this part that we list, we mention other concept here, requires that we put here the keyword requires once again. But there are much easier way to do that. We could just say that coupe must model a car, and it must not be a convertible. So let's look for some other example. So we still have a complex nested requirement here. We have two classes here, Droid and Droid v2. Both has a clone function. Here we have a typo because this one it's called clones, but we have this concept clonable, and it requires that this C type, so this clonable parameter, must have a function, must have a method called clone, and we also require that whatever is returned by the clonable clone is the same as the passed-in type. And for example, this concept would help us to catch the error that the clone of droid v2 returns a droid instead of returning a droid v2, because they are not the same. But again, well, we'd have an easier way to express that. So again, we have a simpler option, because after all, we just want to create a requirement. We just want to have a constraint on the return type of this clone method. So here, this way, we both model that clonable has a method clone and that it returns the same type as C. So this is the same slide that we had before when we were discussing that T blah and U blah problem. So we can use the nested requirements to simulate these Boolean expressions. And here again, it's something that well, you don't need to nest, but you might want to, because what you have on the right side is probably more explicit than or more understandable compared to what you have on the left side. You have the option to choose. So again, here comes an example where the nested requirement is not mandatory, but you might consider using it for readability purposes. So we go back to our has power concept. And before we used there for the exponent an integer, but in this case, we want to have some constraints on the exponent as well. So base must have a method power that takes the exponent, and you might want to constrain that this exponent should be an integral. So in this case, you have to, if you want to use this concept within the requires clause, then you must repeat, you must nest the requires keyword. You might argue that this constraint std integral exponent can be moved outside of the requirements of this outer requires clause, and you could say that has power equals std integral exponent, and we require that base.power takes an exponent. That's right. You can do that. Here it's a question of readability. It's a question of what you think is more readable. But you have the option. So let's see now some let's see real life examples. Let's see how you might want to use concepts, how they can help you in your code base. So let's say you have some utility function in your application, and you want that that function takes only numbers. And for the sake of example, we constrain ourselves only to built-in numbers. So you might want to say that we create this concept number that is an integral or a floating point. But there's as I mentioned, there's a problem with this concept, because well, on the floating point part you are fine, but on the integral part, well, Boolean or characters and and all the character types, they are also considered integral. So if you want to add the true and false, it would work, and you might not want to have that. So you should, in this case, you should forbid the unwanted types. So we are better to create a concept number which is either an integral or floating point, but it's none of these types. It cannot be a bool and any of these characters or an unsigned character. And then when you try to call this add function with two booleans, then you have a nice error message saying that well, when you try to replace A and B with booleans, that doesn't satisfy the constraints you defined with number. So that's a simple way to model this concept number. And I see that there is a question going back to the convertible slide. Why don't you need the parents in and convertible? So let's go back there. So this one, and this one, because here we are defining a concept, and here this works. But in the other examples that we had, so if I go back to such an example here, for example, you don't define a concept, you list your constraints. Here you list your constraints for this template type, for this requires method, and that's different from writing your own constraints. Does it answer your question? Okay. You're welcome. So let's go back to our real life examples, and let's talk a bit about utility functions, because Well, I'm not sure, but I think that many of us worked with applications which have, well, okay, hundreds of thousands of lines of code at least, and they have many utility functions which are templates. They have no assertions at all. The template parameter names are usually just T, U, and well, any other single character names, and there are no documentation. And if you are unlucky, maybe even the name is something that doesn't really help. And you really have to dig into the implementation of that function to understand what it does, to understand what kind of parameters does it expect. And that's a tough situation. You have to waste too much time on trying to understand the code in those cases. But you can use concepts to turn such poorly documented utility functions into self-documenting code. So in this example, we define a concept. So BO means here business object. I just wanted to abbreviate for the sake of fitting to the slide. And you create this concept. So it's a business object with some encodable stuff. And you can require your interface here. So you say that this BO should have an interface A, should have an interface B, it should have an interface C that must return some type. And then you can use whatever way of using concepts with your template functions. In this case, we just use this abbreviated function templates. And as you can see, well, we did two things. We don't use unconstrained type names anymore because, well, we have this business object with encodable stuff T, and we have our own requirements on that. And we also don't use these T's, naked T's, because, well, we both have a constraint and we don't use a single character name. We use something that that explains what we expect there. So you might say that, okay, you still have to read and understand the concept itself. And it's true, you still need to read something, but all the information you need is at one place. And you can move as such some domain knowledge as well into the code by using the good names for the concept name, for your parameters, whatever. And I know that there are some people who advocated that, well, concepts should be mostly used with libraries. And application developers shouldn't really use concepts, and anyway, we should use only the standard concepts, what is shipped with the standard library. But we all can find good examples in our own code base where applications can be turned into something more maintainable, something more understandable by defining the right concepts. Now, how to define the right concepts, that's another question. Probably it would take quite some time, quite some iterations to have the concepts right. That's something that Jeff Garland discussed yesterday for quite some time. So it's not easy to write the good constraints, and it will It will take some time for all of us to learn what is good, what is not good, but we should definitely go and start using concepts and turn our code into something something more maintainable, something that documents itself better than before. And in the previous example, we used the name concept, but even, well, sometimes you use a lambda function because you don't want to bother naming it. You don't want to put it somewhere because you don't really know where to put it. You don't really have a good place for that lambda function. So you just define it unnamed, you define it on the fly. And it might be the same with this previous concept we saw, this object with encodable stuff. Well, you might not want to define that because you only want to use it once. So in that case, you don't have to do. You can just simply use you can use a constraint. You can use it as a requirement for your function template. And as you can see here, well, this is not a typo. We have the requires keyword twice after each other. We need the nested requires clause because otherwise we couldn't use this BO with encodable stuff underscore T parameter in an unnamed context. So outside of a named concept, we couldn't use it in this requirement otherwise. So for me, it's a bit similar to like using a lambda function. And here, still, we gain something because you don't have to go into the implementation. You don't have to read through this and code some stuff, which according to our experience, it might be like hundreds of lines of code or even more. You don't have to go through that to understand what kind of parameter is expected. You just check the requirements, which is always, on the top. And you know what is expected. It's documented as code. So it's time for conclusion. Today we learned about concepts. We learned that we are here for us to validate template arguments at compile time, which was like already possible before, but we didn't have a reusable and scalable way to do that. Now we have it with concepts. And well, the standard library already gives us like about 50 quite generic concepts that we are free to use. In fact, the core guidelines recommends us to use these generic concepts, the standard concepts, whenever it's possible. But we also saw that there are plenty of ways to define our own concepts. And I think we can agree that writing concepts is quite easy. It's quite straightforward. Now, I don't want you to leave with the wrong impression. I said it's easy to write concepts. It doesn't mean that it's easy to write good concepts. So that's something we mentioned just a few minutes before, that making the concepts right is difficult. And if you haven't attended the talk or talks of Jeff Garland yesterday, I would urge you to check the recording as soon as it's available. It will probably take multiple iterations for us to write a good concept. We'll try different things, and maybe it will be too constrained at first, or maybe it will be not constrained enough, or we'll simply find it that, okay, it's not what we really wanted. It's okay. The core guidelines already phrases quite a few recommendations, but we don't have the best practices yet. So concepts are quite new, and many of us don't even have access, at least at work, to the right version of compilers, and hence we don't have the experience. And the experience cannot be replaced by recommendations, by the core guidelines. Well, I don't say they're not important; they are important, but they go as far. So we need to get that experience. So I think that we should start using concepts as soon as it's possible for us. As soon as you switch to C++20, you should go and start using your concepts. Even if some people say that you shouldn't do that, you shouldn't bother with concepts because it's for libraries, because it's for people who really understand what they know. Well, we saw some examples where concepts can be really helpful to turn your application code into something more maintainable, into something, well, let's say live documentation. They serve as live documentation. And even like if you don't have access to C++20 and to concepts yet, I would say that at least, at a bare minimum, we should stop using those names like T and U, what I used often on the slides for brevity. But in real code, we shouldn't do that. We should use better names because they carry a meaning, and that's one of the very important parts of concepts as well. They carry a meaning. They also carry some semantics that is important to define good concepts. Thanks for your attention. It's time for questions. Let me check the different channels. Is it any compiler time overhead or implementation difference between defining of concept in function and just use nested requires? As far as I understand, there is no implementation difference. As far as I saw, I have no measurements for compile time overhead. That's an interesting topic that that we could check after. Actually, I will check it later. I don't know how to come back to you. So thanks a lot for your comments. There was that question: how can I partially order atomic constraints? Thinking about it, sorry, I don't have the answer. I don't know. I will have a look into it, and we can continue discussing offline on Discord. Just ping me. So thanks a lot for attending this session, and see you soon.